this is the biggest part of the process that is going to be new. And that is that if we talked about we can use the z-scores and all that formula when we know the population standard deviation. And then I said, most of the time, we won't, because we'll get our standard deviation from what the sample is. And so let's talk about when we only know the sample standard deviation. When we only know the sample standard deviation, then we're going to use a distribution that is slightly different from the usual normal distribution. We'll have a new statistic that is still value minus mean over standard deviation, but this will have a slightly different distribution, and it's going to be called a t distribution. Slightly different shape, still symmetric, still has a peak at 0, but has more area in the tails than the usual normal distribution. And so here's the larger area in the tails. Right, t-score will tell us how far we are, how many standard deviations we are away from the mean. Same way as z-score does. It's computed the same way. However, there's a different t-distribution for each sample size. And guess what? As the sample size is going to get bigger, guess what's going to happen to the spread of the t-distribution? It's going to get smaller. Right, that's what we talked about for as sample size goes up, standard deviation goes down. Where is my, oh, here we go. So here is a t-distribution with a sample size of 2. Here's a t-distribution with a sample size of 9. Here's what the normal distribution looks like. So it's very close to a normal distribution, but not quite a normal distribution. So similar to the standard normal distribution, bit greater, more probability in the tails, and less in the center than the usual normal distribution. And as sample size increases, we get closer and closer to a normal distribution. And it's going to basically be a normal distribution when we get to a sample size of 30. When our sample size is at least 30, then we'll have normal approximations. So, depending on the sample size, the distribution is going to look slightly different. Therefore, the t-score, the critical value that I use in my confidence interval, is going to be slightly different, depending on the sample size. And what we're actually going to put in the calculator or look at the table to determine is going to be something called degrees of freedom. And the degrees of freedom is basically how many elements in my set of numbers are free to vary. And so that's going to have a certain formula, but let me give you some examples just so that we have an idea of what this formula is going to be. So there we go. Just some space to write. Let's say that I want my mean to be 5. And I want you to tell me at what point can I guarantee and know what all the values are in my distribution. Okay? So let's say that I have a sample size of 1. And the mean of that sample is 5. Can you guarantee me what the number has to be? What my one size sample is? My list is 1 my list has one thing in it, and the mean is 5. What is it? It's got to be 5, right? So it's got to be 5. So how many degrees of freedom do I have in that list? How many numbers are allowed to vary and be different before I lock in and say, here's what the number has to be? Well, it has 0 degrees of freedom. Because the only possibility is that it has to be 5. It's locked in to be 5. Okay, let's take a sample size of 2. Instead, the sample size is 2. So I have 2 numbers. The mean is 5. Can you guarantee me what the 2 numbers are? No, not yet. What if I told you the first number in the list was 3? Can you guarantee me what the second number is now? Yes, you can. What does the second number in the list have to be in order for the mean to be 5? Add up all the numbers and divide by how many there are. And I want that to be 5. 7. So my second number in the list had to be 7. So how many degrees of freedom did we have? We had 1 degree of freedom. I had to tell you one of these numbers on the list before the second number was locked in. And I knew what the number had to be. Let me do one more. N is 3. There are 3 numbers on my list. Can you guarantee me what the 3 numbers are? No. What if I tell you the first number in the list is 4 and there are 2 more numbers on the list? Can you guarantee me what the other 2 numbers are? No. What if I tell you the second number is 6? Can you guarantee me what the third number on the list is? Yes, we can. The third number on the list has to be what? 5. So, degrees of freedom. How many numbers on the list were free to be whatever before we said, oh, this is what the rest of the numbers on the list have to be? It was the first 2. And so, that is what degrees of freedom is. And the formula for degrees of freedom is always going to be whatever our sample size is minus 1. So in other words, if I have a sample, if I have a list of numbers, and I know what the mean is, all the other numbers on the list are free to vary except for that last one before the list is locked in and has to come out to be that number. So that's how we get degrees of freedom being n minus 1. Okay, any questions? I saw some hands up. And I wasn't sure whether we were wanting to ask a question or volunteering answers. So remember how so the question is like, how does this fit into our t-score picture? Remember how the different sample sizes give us slightly different distributions? And so that means one of the things that we need to tell the calculator is what sample size did this come from? And the way that we're going to do that is by telling it the degrees of freedom, which is going to be n minus 1. So in a sample size of 10, we're going to tell it like what percentile we want, just like we did with our z-scores, but we also need to tell it our degrees of freedom, which in that case would be 10 minus 1, which is 9. So let's do a little bit of practice with using this t-distribution. We did that slide. Yep. Okay. Suppose you want to construct a 95% confidence interval based on a simple random sample of size n equals 12. What critical value should you use? Well, let's cover the calculator first. So make sure you have out your calculators. Okay. So there's two different ways to do this. Just like with z-scores, you can do this with a table with z-scores, or you can do this on the calculator. So on your calculator, you're going to go to the same menu that you would go to for z-scores, which is going to be second vars for distribution. And since we've got a percentile and are looking for the and we're looking for the specific t-score, remember that would have been inverse norm with our z-scores, so now it's going to be inverse t. And then going the other way from our t-scores to getting a percentage would be t-CDF. So we're going to go inverse t. Is there anyone for whom inverse t is not there on the calculator? Okay, just want to make sure. So inverse t. Area. Our area here for a 95% confidence interval, remember it's not 0.95, it's going to be 0.95, and then our tail on the left, since this is my percentile, so 2.5%, so 95% in the middle plus 2.5% on that left tail is going to be 0.975. Our sample size is 12, which means our degrees of freedom is going to be 12 minus 1, which is 11. If it just says inverse t and then gives a open parentheses, then this is what your thing should look like. It should be the area to the left, comma, degrees of freedom. And there's your t-score. Basically 2.2. If you don't have that in your calculator, which I know some people in this class have an older calculator, then you can use a table. This is in the back of your textbook, or if you're more comfortable with the table. What this table looks like, just to give an idea. Along the columns are upper tail probability. We're going to use this part of it next chapter. What we're going to use here is confidence level. So we want a 95% confidence level, so that means we're interested in this column. And I'll zoom in a little bit. So this column is what we're looking at, and our degrees of freedom was 12 minus 1 was 11. So we look at 11 degrees of freedom, and there's the 2.201. And so that's how we would do it with our table. With the calculator, it's inverse t, give your percentile, give your degrees of freedom. And this is one more extra piece of work that we need to show in the overall structure of the confidence interval. You should say what your t-score is and show how you're getting your degrees of freedom. That's basically the only thing in this process that is new. Pretty much everything else that we do is going to be the same. It's just going to use means instead of proportions. So let me outline how that's going to look, and then we will do an example here. So just to make that table a little bit bigger, that's what it would look like. Either way, you should get 2.201. All right, let's zoom out a little bit, because that's the detail that is very different from what we did with proportions. Now let's zoom out and talk big picture. First off, remember that our general structure is a statistic plus or minus the critical value times standard deviation. So all these pieces are going to look a little bit different. First off, the statistic we're using is a mean instead of a proportion. So instead of p hat, which we did before, it's going to be x bar. Plus or minus the critical value, now instead of a z-score, we're using a t-score, times the standard deviation formula. Well, the standard deviation formula, instead of square root of pq over n, now we're using standard deviation divided by square root of n, which is our standard deviation formula for means. We learned that last chapter. So the only difference is that now we're using all the formulas and conditions and all that stuff for means, and we're using t-score instead of z-score. And so jumping forward a little bit more, we still have our three conditions that we're going to check. The biggest difference, it's still random, normal, and independent. Random and independent are going to be the same. For normal, instead of n times p and n times 1 minus p, we're going to check that our sample size is at least 30. Everything else is going to be the exact same process. We're going to state out, we're using a confidence interval to estimate, and then we're going to define what our mean is that we're finding. We're going to check these three conditions. We want to make sure the sample size is at least 30. Calculate, using that new formula. Interpret, it's going to be the same sentence as it was before. You had a question?
So we're going to use t-score for every single time we calculate the interval for a population.
For means, almost all the time. If we are told what sigma is, the population standard deviation, then we use z-scores. Otherwise, we use t-scores. And usually, we're not going to know what the population standard deviation is. It will usually be given to you, or you'll get a list of numbers, and you can do one variable stats to find it very quickly. And then here's your process of step 3. That's the formula. You already wrote this down. You already wrote that stuff down. Okay. All right. One second. This example's in the book, so I'm going to read it. We're going to try and get through this whole process here. Manufacturer of a high-resolution video terminal must control the tension on mesh-refined wires that lies beneath the surface of the viewing screen. Too much tension will tear it, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. So, here are the tension readings from a random sample of 20 screens from a single day's production. And then it gives the 20 values. Construct and interpret a 90% confidence interval for the mean tension of all screens produced on this day. Okay. So, we'll notice a couple things already. First off, a list of values is given to us here. So we're going to talk about how that works. Secondly, you'll notice that I said the sample size was 20, which is not 30. So we're going to talk about what happens when the sample size is less than 30 and what we need to do. So those are going to be the kind of key parts that I'm going to highlight. Everything else I'm going to kind of breeze through a little bit. So first off, in your calculators, I want you to put in this list. It's on page 508 if you want to put it in yourself. Otherwise, you can follow along with the values I'm putting in. Man, we haven't used lists in a while. Okay, there we go. $269.5. If what I say and what I put down is different, then let me know, just to make sure I'm putting everything in right. 297, 269.6, 283.3, 304.8, 280.4, 233.5, 257.4, 317.5, 327.4. That should be the 10th value. Am I good so far? Okay. Keep double checking me here. 264.7, 307.7, 310, 343.3, 328.1, 342.6, 338.8, 340.1, 374.6, 336.1, and that's the last value. All right, back to business. All right, so I'm going to go again and calculate one variable stats. And these are the values I should have. The values that I want to take from this, first off, my sample size is 20. I need X bar. And I need S sub X. Those are the two values that you want to write down. And I usually have people write those down in step 1 so that they have them. All right. I'm going to give you a bit of advice here. Focus on, because I'm going to do this quicker than you can write down. Focus on watching the process happen. And then if you need to go back and write something down, the video will be here. It'll all be up there. Step 1. We want to estimate 95% confidence interval for the mean tension of all the video terminals. So we used mu because we're saying that we're estimating the population mean, and then we're defining what mu is. This is also where I would write down the mean and standard deviation. There's step 1. Questions on step 1. All right. Step 2. We check our conditions. Random. It says the tension readings from a random sample of 20 screens. So we do have a random sample happening. Normal. Here's a key part that I want to pause at. If, and you do not need to write all of this down, because there are about to be some graphs put in front of you here. Since the sample size is less than 30, what we're going to check for is that the more skewed the original distribution is, the more that the sample size matters, right? So what that means is if we have a sample size at least 30, then we're going to have normal distribution no matter what. If we have a sample size less than 30, we need to check that a normal distribution seems about right. So we need to actually rely on the actual distribution of the sample. And we can get all of these different tables out of the calculator. And then 10% condition. There are at least 200 different terminals. Let me go back to these 3 graphs. You can get these all out of your calculator. The first value here is a dot plot. And we're looking, and the second one is a box plot. These two, we're looking for relative symmetry. And especially in the box plot, we have a fairly symmetric distribution. The third is a normal probability plot. A normal probability plot, I may have talked about this very briefly in chapter 2. A normal probability plot puts all the values on the x-axis and the z-scores of those values on the y-axis. And if the distribution is normal, then this graph should be about linear. That's what this graph should look like if we have about a normal distribution. So as long as this graph looks fairly linear and my distribution looks fairly symmetric, then we can be okay with the normal distribution. And we only need to check these graphs if the sample size is less than 30. If the sample size is greater than 30, then we're good to go anyways. So let me show you on the calculator where those are going to end up. We go second and stat plot. I won't have you graph all these, but just to remind you, the 2 main ones that you would use is the box plot with the outliers graphed, and then the one on the far right is the normal probability plot. So I can go normal probability plot for list 1 and then go zoom 9. Hold on. I have a calc thing happening up here. Which is messing with it. Let me turn that off. Zoom 9. Let's try that again. Oh, I forgot to turn it on. That's what happened. This needs to be on. How about now? There it is. It should be about linear. There might be little curves here and there, but fairly linear is what we should see. So again, that's the option on the far right of my graph options. let me finish this problem. Step 3, calculate. And it's going to be, step 3 is going to follow the same process of formula, plug in the numbers, answer. The only thing that's going to be added is that we're going to have the t-score. And I changed my mind. I'm going to finish it tomorrow. I don't want to breeze through this that fast. So we'll finish up this problem tomorrow. Aiden.